Welcome back, everybody, to eCoreAcademy. My name is Anita and I am one of the teachers and co-founders here. Today, I have a new Algebra 2 lesson prepared for all of you. I know a lot of you have been waiting for me to make a new lesson for a while now, so I'm really happy to have come off of my 1-week break to start making lessons once again. Again, like I said, this is an Algebra 2 lesson. It is going to be a continuation of the last lesson I made on quadratic functions. The last lesson I made was an introduction to the quadratics unit we will be doing in Algebra 2. I know a lot of you may have done quadratics in Algebra 1, but this is a continuation of what you learned of the fundamentals of quadratics in Algebra 1, and we look at them through the scopes of higher level math students in Algebra 2 in this unit. So this is going to be quadratic functions and transformations part 2. The last video we did an introduction to quadratics in Algebra 2. This video is going to be looking at translations of quadratics. So translations are types of transformations where we shift the graph of a function. We shift the parent function and we move it to different parts of the coordinate plane by manipulating the quadratic equation. So that's what we're going to be doing today. Before I even get into the video, we would really appreciate it if you paused and liked the video to support me and my brother as teachers on eCoreAcademy. Also, subscribe to the channel to join our amazing student community. Also, hit the post notification button and also look into our social media in the description box below and follow us on there and use those socials to share our videos and our channel with your friends and family. And lastly, drop a comment down below of what you thought of the video. Okay, let's get right into the topic I have prepared for us to look at today. So we're going to look at quadratics in real life. In the last video, we did the same slide to start the lesson off. Instead of the two examples I'm going to show you, we did a human cannonball, where there was a cannonball that launched a human and a parabolic shape. So the arch shape that we saw of the parabola was the path the human cannon followed through the air. So let's see the two examples I have prepared for us today. Okay, so the first one here is called the moon bridge. So if you see with my pen, I just drew that kind of general shape of the bridge. It's called the moon bridge because if you see, it kind of looks like the moon, and the moon is symbolic in Chinese and Japanese Asian culture. This bridge is usually found in ornamental gardens in China and Japan, and it's native to those areas. But the reason I wanted to bring this up is I wanted to ask you, can you see the parabola in this moon bridge? So a parabola looks kind of like this on a coordinate plane. That is what a parabola could look like, and the parabola could look like this. It's just an inverted parabola reflected across the x-axis. So these are what parabolas could look like. Well, can you see any kind of parabolic shape in this? Well, I can. So let's draw it right here. I'm drawing it in red. So that is kind of what the parabola looks like in this bridge. So this moon bridge is a real-life quadratic. It looks like an actual parabola. So let's see the other example I have. This is a roller coaster. This is actually these are like the roller coaster carts where you get in and you just go along the roller coaster. So these are the people. And this is the actual roller coaster, the structure right here. So the question I have to ask you regarding this picture is, can you see the parabola in this roller coaster? Well, I can. It's also the same reflected over the x-axis parabola that we see in this moon bridge, and I'll just draw it out for you as well. So it very much looks like a parabola. Yes, so that would be the parabola of a roller coaster. So these are two quadratics in real life. If you see with the moon bridge, it looks like a inverted parabola. And with the roller coaster, it also looks like one. These would be reflected across the x-axis. And you can see they both look like parabolas. These are quadratics in real life and their real-life applications. Okay, let's get right into the content we have today, aside from that. Let's review some key concepts before I even get into more advanced concepts. So given that y equals ax squared, the following statements are all true. So if you look at this y equals ax squared, this is like the general form of a parabola. So the parent function of a parabola is y equals x squared. Now we have this a in front of it. So we'll see what a does to this parent function of a quadratic. If a is greater than 0, the parabola opens upward and has a minimum. So let's break down what this means. So this is the key concept you want to take away here is a is greater than 0. So what does that mean? Well, a can be equal to 1, can be equal to 2, could be equal to 100. So a has to just be any value greater than 0. It cannot be equal to 0. So the parabola opens upward. So what does this mean? So if you're thinking of a parabola, the parabola opens up. It's like a U shape, and it can this is one way it can open up. Here's another way it can open up. I showed both of those to you. Either it's reflected over the x-axis or it's not. So what does it mean by opening upward? Well, if I hold my hands this way, which way does it open? Which way are we opening it? So if you think of this as a container and I was like catching rain in my hands, which way do my hands open up? They open up upward. If I hold my hands this way, which way does this parabola open up? It opens up downward. So in this example, the parabola opens up upward. So what would this parabola look like? Well, it would look like this. That's how that parabola would look. And this parabola has a minimum. So if you remember we were talking about the vertex is this point right here that divides your parabola along the axis of symmetry perfectly in half. So your vertex is going to be a minimum, which means your vertex is going to be the smallest value your parabola could possibly be. If you see, this is the lowest point of the parabola. So if this a right here is greater than 0 in your quadratic equation, the parabola opens upward like this, and it has a minimum, meaning the vertex is the smallest value your parabola could possibly be. Your vertex is right here. Let's look at the second point. Okay, so if a is less than 0, the parabola opens downward. This says downward. I'm sorry, I drew a little bit over it. That means it's reflected across the x-axis, as we were saying. This is an important thing to consider. It's reflected across the x-axis, and it has a maximum. So if a is less than 0, what can a possibly be? Well, a could be equal to negative 1/2. A could be equal to negative 5. A could be equal to negative 1,000, for all we know. It's just all these negative values. Anything less than 0, it can't be equal to 0, but anything less than 0. So all your negative numbers, it can be integers, they can be non-integers, whatever is less than 0. So what does this mean? So the parabola opens downward. We just said if the parabola is shaped like this, a is greater than 0, and the parabola opens upward. If a is less than 0, meaning it is a negative value, the parabola opens downward, meaning it looks something like this. I'll even draw it off to the side right here. Your parabola will look something like that. And it's called reflection over the x-axis. So if you see this negative sign right in front of your a value, like you have here negative 1/2, negative 5, negative 1,000, then you should automatically know your parabola is flipped upside down. That's what that negative value at the very beginning of your quadratic equation means. Your parabola is flipped upside down. And what we call that in math is reflection across the x-axis. So instead of saying the parabola is flipped upside down, to say it in more mathematical terms, you would say the parabola is reflected across the x-axis. And if you see the vertex, which is right here, dividing this parabola in two symmetrical halves, it is a maximum. This is the largest the parabola will ever be. Then the parabola just goes downward. So this is like the peak. This is the largest the parabola can possibly be. The largest y value will be located at your vertex. Okay, let's look at the last point. As the absolute value of a increases, the parabola stretches vertically. So let's break this down. So the absolute value of a. So let's make sure we know what absolute value is. So the absolute value is a number's distance from 0. So your absolute value is always going to be positive. So if I say the absolute value of 2, well, how far is 2 from 0? Well, 2 is 2 units away from 0, so the absolute value of 2 is 2. How about the absolute value of negative 2? Well, negative 2 is also 2 units away from 0. So the absolute value of negative 2 is also 2. You should remember this from 6th grade math all the way to algebra 1. So what does this mean? As the absolute value of a increases, the parabola stretches vertically. So here we would disregard this negative sign. So as the absolute value of a increases, as meaning it gets bigger, like 5, 10, 15, 100, 1,000, 1,500, whatever your value is, the parabola stretches vertically. let's look at the opposite. So the opposite would be if the absolute value of a decreases, the parabola does not stretch vertically, it compresses vertically, meaning you would be going backwards. You would be going 1, 0.5, 0.25, 0.025. The smaller it is, the fraction, like the smaller fraction you get. Here we'd be disregarding the positive or negative value of a in this case. So remember that. So what does this mean? Well, the larger the absolute value of a is, the parabola is stretching vertically. So vertically means this way, horizontally is this way. So if I drew a graph of something like this, if I drew a graph of something with a large if a large value of the largest absolute value of a, it would look something like this. It would be stretched vertically. So it'd be a very skinny looking graph. So if my equation was something like y equals 27x squared, 27 is a pretty big a value. So it would be stretched vertically. So vertically, it's like very long. However, if I had something the opposite, if I, instead of saying y equals 27x squared, if I said y equals 1/2 x squared, it would be, I don't want to say a fat graph, but it would be very much stretched out. So instead of being a really long, skinny, vertically stretched graph, it'd be a more squat looking graph, like a fatter looking graph. So it looks something like this, and we would call that vertically compressed, because if you see, it's pressed downward vertically. Think of a short person, they're being compressed. So it's just compressed this way. So that's what we would say. So this might be a graph in which the absolute value of a is pretty large. This might be a graph in which the absolute value of a is pretty small. So that's how we interpret that. And I'm sorry, I wrote right below it, as the absolute value of a decreases, the parabola compresses vertically. So these would be the examples. So this statement is proving this, and this statement down here is proving this. So let's go to the next slide. Okay, everyone, let's transition into maximum and minimum values. For many of you who are confused about the vertex and the peak or the lowest point of the parabola, let's go over it right now with maximum and minimum values. So the maximum and minimum values, as maximum and the word minimum mean, are the highest or the lowest point on a parabola. So let me draw two parabolas right over here. This is going to be this one right here is going to be like your average parabola, and then this one will be where the a value is negative and it's reflected over the x-axis, as we just reviewed in key concepts. And this right here would be your vertex, and this right here would be your vertex on this parabola, and here's just the dotted line denoting the axis of symmetry, splitting these parabolas into two symmetrical halves. So as we have written right here, highest or lowest point on a parabola. In this graph to the left, your average parabola, if you see your vertex, well, it's the lowest point on your parabola. It's the bottommost point, the lowest point on your parabola. These two arrows right here, they're extending upward and away. So they're extending upward into higher and higher values. Your vertex here is the lowest value. So in this graph, your vertex would be your minimum. So this graph has a minimum vertex, minimum value. However, this graph is the polar opposite. It's the graph that opens downward and is reflected across the x-axis. In this case, the vertex is the highest point. It's your maximum. If you see, these arrows extend downward. This is the largest this graph can possibly be. These arrows extend downward into lower positive values and then eventually into your negative values. So this is where we would call this a maximum. Okay. In other words, the vertex represents the largest or smallest value of the parabola. So the important word here would be your vertex. Your vertex is very important when it comes to your parabolic graph. Like I just said, it represents the largest, which is your maximum. Let me just write maximum underneath it. Maximum, or your smallest, which is your minimum value of the parabola. So your vertex pretty much denotes these two values. Remember, the maximum or minimum is always the y value of the vertex. So if I said my vertex if I have a random parabola and I told you my vertex is, you always give the vertex as a point, because the vertex is a point on the graph of the parabola. If I said my vertex was -1, 2, well, If I asked you, okay, what is the maximum or minimum value? In this case, we don't see the actual parabolic graph, so we wouldn't tell you exactly what if the parabola had a maximum or minimum. But if I just asked you, what is the value of the minimum or maximum? Well, we know the minimum or maximum actually is the vertex of a parabola. So in other words, I'm asking you, what is the vertex of this parabola? Well, you wouldn't just give me the coordinate that I've written right here. You would give me the y value, because remember, if you have a coordinate pair, if I'm asking you what the value of the graph is at the maximum or minimum, the y-coordinate is the value of the graph. So you would be giving me 2. You would be telling me that the maximum or minimum of this quadratic equation is 2. Since, like I just said, the y-coordinate is the value of a function at a given point. So if I asked you for the value of a function at a given point, you would give me the y-coordinate, because that coordinate denotes the value of the function. That's why we write y equals. Y is the value of the function. So that's how you would tell someone the maximum or minimum value of a quadratic equation. Okay, let's go to the next slide. So I'm going to give you a translations problem, and then we're going to work through it together. So here's the actual problem. Graph y. I'm going to give you 3 equations to graph. The 3 equations are y equals x squared, y equals x squared minus 3, and y equals x plus 4, and that whole quantity squared. And you're going to graph them all in the same coordinate plane. So you're going to have one coordinate plane with the same set of axes, and then you're going to graph all 3 of these on the exact same coordinate plane. So let's just underline these three quadratic equations that we're asked to graph. They're all quadratics because if you see, they're all raised to the exponent of 2, 2, 2. If you see, they're all written in different ways. This one is kind of plain. This is what we would call our parent function. Our parent function, if you all remember, is the simplest function in a function family that still retains the properties of the graph of that function family. So this equation is the simplest possible quadratic equation that you would find, other than y equals negative x squared. But this is even simpler than that. This is the parent quadratic. This here is y equals x squared minus 3. So the x term is squared, and then you just have an additional minus 3 after that. Here we have this whole quantity, x plus 4, but that whole quantity is squared. So that's kind of special. This one has a set of parentheses. This one does not, on the same coordinate plane. So those are going to be our 3 equations. Then we're going to be using our TI to graph. And I'm going to be showing you how to do that on the TI calculator. Afterwards, going to be identifying the vertex, the axis of symmetry, the domain, and the range of each of these graphs. So we're going to be identifying these 4 things for each of these graphs. And then after that, we're going to be comparing the graphs to one another. So we're going to be really understanding the properties of different quadratic equations in this. Okay, before we even get into the solution, for many of you who I may have lost, I added this additional section. So what do we need to do? So what do we need to figure out? So whenever you're approaching any kind of math problem, especially if it's a longer math problem, you always want to ask yourself, what do I need to do? What is this math problem asking me to solve? So this is what I've broken it down into. So you need to find the following. You need to graph the 3 quadratic equations. So grab a coordinate plane. If you have your TI, that's great. If you don't, then grab some coordinate grid paper or lined paper, whatever works. So we're going to be graphing these 3 equations. And then after that, we're going to find each one's vertex, axis of symmetry, domain, and range. So for each of these, we're going to be finding these 4 components. And then lastly, we're going to be comparing the graphs to one another. So these are like the 3 steps to solving this translations problem. All right, let's switch over to the next slide, and I'm going to bring up the digital TI calculator onto my screen so we can look at it together. I just went to the next slide where I have the solution to the translations problem I showed you on the last slide. I promised to show you how to do this on the TI calculator. So if you want to skip that tedious graphing using a coordinate plane and XY table and doing all the computation by yourself, follow along. I have a TI calculator emulator, which is exactly like the TI calculator that I show you on the screen in previous videos up on the screen. So please follow along, and I'll show you first how to graph these 3 equations. So let me show you how to graph this on the TI. I'm going to move this over. And first, let's look at this graph to the right over here. This red parabola is your parent function, y equals x squared. The blue parabola that overlaps it somewhat and comes a little bit lower is your y equals x squared minus 3, the second equation I showed you. And this green parabola to the left over here is your y equals the quantity of x plus 4 whole squared. That is this green parabola. This is just the end product of what we're going to get, but let me first show you how to do it on the calculator. I'm going to show you the buttons, and on the right side, on this right panel, the actual button list of buttons I clicked will come up, so that will be also helpful for many of you viewing this. So first, we want to go to our y equals, so we can input these quadratic equations into our y equals so they can be graphed. Our first is our parent function, so first we're going to hit the x, of the special numerals key, then x squared. And then we're going to hit the down arrow and come to our y2. And here we are going to hit x again and then square that, and we need that -3. So we're going to hit minus, and then we're going to hit 3. Then we're going to hit the down arrow to go to our y3 for our final equation. And for this, we're doing this green equation over here. We need to put open parentheses, x plus 4, close parentheses, and then hit that x squared so that whole quantity is squared. Then we hit the graph button to see each of these equations graphed. The blue is your y equals x squared. The colors are a little bit different on the calculator, so I'll just name them. And this red is your y equals x squared minus 3, and this kind of black right here is y equals x plus 4, that quantity squared. So this is how you would graph it on the TI calculator. Okay, so I put the TI calculator away, and we're going to be working through the second part of this translation solution. So first we graphed it. Now we got to answer some questions about the properties of these quadratic equations. So red, again, I just want to go over this key I've written up here. This red parabola is your y equals x squared. The blue one is your y equals x squared minus 3, and your green is y equals the quantity of x plus 4 squared. So now we're going to be walking through the properties. First, let's go over red. Red is your parent function, y equals x squared. The vertex is right down here. It is the minimum of this parabola because this parabola opens upwards. The vertex is 0, 0 because if you see the vertex is located right at the center of the coordinate plane at 0, 0. Your axis of symmetry, the line that divides your parabola perfectly in half, is going to be the x-coordinate of your vertex. And it's going to be an x equals value because it is a vertical line. Remember, x equals something is a vertical line. So in this case, it's x equals 0 because it's pretty much the y-axis. When your axis of symmetry is the y-axis, it is x equals 0. The domain is negative infinity to positive infinity, because if you see here, this part of the parabola, your negative side just extends onward and onward into all possible negative x values, and then your positive side of your parabola just extends onward and onward into your positive set of x values. So this would be the case. This holds true for all quadratic functions for parabolas, any case. Your domain is always going to be negative infinity to positive infinity, so please remember that. And lastly, your range is going to be your minimum is your vertex. It's going to be 0. So that's the smallest value it can be. And we put a bracket here because remember, interval notation, we use this to show domain and range in higher level math. It's 0 because that is the y coordinate of your vertex. Your vertex is your minimum, and that's the smallest it's going to be. So 0, and then it just goes onward into positive infinity. Okay, so let's look at the blue equation. So y equals x squared minus 3. Your vertex in this case is 0, negative 3. It's just the point where the vertex lies right here. Your axis of symmetry is also x equals 0 because if you see your y-axis is your axis of symmetry. The domain is negative infinity to positive infinity, as that's the case with all quadratics. And your range is negative 3 with a bracket to infinity. Negative 3 is included. It's the lowest point of your parabola. It's the smallest y value, so it's from negative 3, and then we just continue on into positive infinity. Now let's look at the green and the final equation. The vertex is right here. It is the point negative 4 and then 0. Your axis of symmetry is negative 4. It's this vertical line right here. It is the x-coordinate of your vertex. Your domain holds the same, and it's true. Negative infinity to positive infinity, and your range is 0 to infinity. Let's look at it over here. The smallest your range will possibly be is 0, which we can see in the vertex, and 0 is included, so we put a bracket and then just continues onward into infinity. Now let's do some comparisons between these three graphs. They all have the same domain. This domain holds true for any quadratic you see, negative infinity to positive infinity. They have different ranges, however. This is 0 to positive infinity, negative 3 to positive infinity, and 0 to infinity, because they all are vertically placed in different places. This one is placed all the way down here, this one's up here, this one is up here. Then we have different vertices because they all have different minimum coordinates. This one here has 0, 0, this one has 0, negative 3, and this has negative 4, 0. Then we have different axes of symmetry. So this one's axis of symmetry is x equals 0. This one's also x equals 0 because it's just along the same vertical line. But this one is x equals negative 4. So it's shifted 4 to the left. So red is the parent function. It's your y equals x squared. It is your parent. It's the simplest quadratic equation you could have. That's part of the family that still has the properties of any quadratic. Blue is translated 3 units down. If you see this negative 3 right here, it's just your same parent function, your y equals x squared, but minus 3 means this has been moved down vertically 3 units. It's been moved downward 3 units. Green is x plus 4 to the power of 2, that whole expression. This is translated 4 units left of the parent function. This we're going to be learning later. This is a horizontal translation. Whatever you have in the parentheses with x, we're going to do the opposite of that. So even though this is plus 4, we're actually going in the opposite direction. Instead of moving 4 units to the right, we're going to be doing negative 4, moving 4 units to the left. And then we'll get green is translated 4 units left. So that's how we solve the translations problem. Let's get into more important concepts, as in vertex form. So translations are the easiest to find when you're given the quadratics in vertex form. And we're going to be looking at vertex form right now. If you're given vertex form, you can definitely identify the translation of the parent function. So vertex form is y equals a times the quantity x minus h whole squared plus k. So we're going to be breaking this down so you understand what each part is. The vertex itself, you're going to be having the vertex as hk. So this value h is going to be your x coordinate of the vertex, and your k is going to be your y coordinate of the vertex. So if you have the vertex of your parabola, you can put that into this vertex form equation, and you'll know most of the equation of your parabola. The axis of symmetry is x equals h. So whatever your x coordinate is, like I told you before, because your axis of symmetry is a vertical line that passes through the vertex, your axis of symmetry is just going to be equal to the x coordinate of your vertex. Notice here we have a times x minus h. So this is very important. I'm going to give you an example. If our vertex was 4, 1, if the k value is 1 and h value is 4, here we wouldn't write it as x plus 4. We would write it as x minus 4. So you do the opposite, as I wrote down here. Opposite of what you see in the equation. So the same holds true if I read it the other way. So if the equation was y equals blah, 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 x minus 4 whole squared, well, how would I write the vertex? Well, I would know the y coordinate is not negative 4. It's the opposite. It's 4. Same holds true if I said x plus 4. In this case, it would be the opposite. So the actual value would be negative 4. That's just how this vertex form works. So now you understand the axis of symmetry. Remember, x equals h. So your vertical line will be equal to the x coordinate of your vertex. It's the opposite, always going to be the opposite of what you see in the vertex form equation. Now I want to do what I call a component table. So the problem is we're going to be completing the following table for each blank space in it. And I'm just going to bring up the table here. And it's called a component table because I'm giving you a quadratic equation, and we're breaking the quadratic equation into its components as listed here. So we're going to break it into its vertex, its axis of symmetry, maximum or minimum value, domain, and range. So we're going to be solving this together. The quadratic equation I am giving you is y equals negative 2 times the quantity of x plus 5 whole squared plus 1. As you can see, this is written in vertex form that I just showed you. So let's break it apart. We can actually answer each of these questions. Think of each of these components as a question, as though I'm asking you, what is the vertex? What is the axis of symmetry? Does this equation have a maximum or a minimum? Does it have what is the domain and what is the range? We're going to actually solve all of these without even graphing the parabola, which is really cool, and I'm going to show you how to do it. So let's first derive the vertex. Well, if you think about it, vertex form is y equals a times the quantity of x minus h whole squared plus k. You're going to have to memorize that, and you're going to have to identify each of these values. So you got y equals -2. -2 is your a. X plus 5, this is pretty much your x minus h squared, plus 1, 1 is your k. So let's bring the vertex. The vertex is hk. So k is right here. K is equal to 1. So we have our y-coordinate of the vertex. Well, what about h? It's going to be found in these parentheses. So x plus 5. So the plus 5 would be our x-coordinate of our vertex. However, remember, it's the opposite. So we wouldn't write plus 5. We're going to write -5 because technically this is x minus h. So you would have to have a -5 to multiply with that minus sign to get an x plus 5. So your vertex would be -5, 1. Now let's get the axis of symmetry. Remember, axis of symmetry is a vertical line. X equals h. So your vertical line is going to be equal to the x-coordinate of your vertex. So your vertical line, which is your axis of symmetry, is x equals -5. Next, I'm asking you, does this parabola have a maximum or minimum? As in, does it open upward or downward? Is it like your average parabola, or is it reflected across the x-axis? Well, come over to the a value that we just learned at the beginning of this lesson. Our a value is negative, which means it is reflected across the x-axis. So we're not going to have a parabola that looks like this. We're going to have a parabola that looks like this. It opens downward, meaning it has a maximum point. It's opening downward like this. So we're going to have a maximum point, and the maximum point is going to be our vertex. But when I'm asking you the value of the maximum point, remember, you have to give me the y value of the vertex, because the y-coordinate is the value of a function at a given point. So that would be 1. Now let's look at the domain. Remember, the domain is -infinity to +infinity for any quadratic equation. And lastly, let's look at the range. Like we just picturing it in our mind, the parabola looks something like this. So the top point is going to be our vertex. Well, it's just going to be negative values up until our vertex. So the largest value is going to be the value of the vertex, and the value of the vertex is 1. So we're going to have -infinity, all these negative values leading up to 1, which is our maximum value. And we're going to bracket it because it's part of the function. So that's how we solve this component table without even looking at a graph of a parabola. So good job. Pat on the back if you're able to do that. Okay, so that's the end of this lesson. I'm really happy to have gotten back to the usual posting schedule, and please be expecting more videos from me. Please like this video to show your support of AJ and me as the teachers, and also subscribe to our channel to join the student community. Use our socials in the description box below to share about eCoreAcademy and help us promote our channel on social media. And also, please drop a comment down below of what you thought. We have a Gmail if you have any business or personal correspondences you'd rather keep private. And lastly, we have a website going up. We're so excited. We're going to be launching it probably in the upcoming week, and it is packed with so much good material. We're going to have our lessons up there. We're going to have our notes up there that you don't get on the YouTube channel. We're going to have an interactive quiz up there that you don't get on the YouTube channel. We're going to have structured curriculums. So if you're trying to do a course, you can follow it in the order that we suggest after we actually have taken these courses. So please, when that goes up, please check that out. And we'll be posting all over our social media promoting that. All right, please have a nice day, and I'll catch you with the next video. Bye.